How many different ways can you reach your destination in a grid, no matter the twists and turns? Unique Paths is a Pattern Mastery 100 dynamic programming classic and a favorite at Google, Meta, and Amazon. Over 30% of candidates make mistakes with state transitions or grid boundaries. Master this and you'll unlock the foundation for nearly every grid-based DP problem in interviews. Let's solve unique paths using the basic approach, so you'll confidently tackle any path-counting DP challenge. Given an MXN grid, count the number of unique paths from the top left corner to the bottom right corner. You can only move right or down at each step. Integers m, n, grid dimensions. Integer, number of unique paths. Picture planning a robot's moves through a warehouse, or a delivery drone's flight plan over a grid city. Interviewers might ask, how would you count all possible routes if movement is restricted to right and down? What's tricky? You can't move diagonally or backward. Many candidates overcomplicate or forget edge cases for the first row/column. Dynamic programming and combinatorics both provide solutions. The robot can only arrive at a cell from above or left. For any cell, I, j, the number of ways to reach it is the sum of the ways to reach I1, j, and I, j1. Initialize the first row and first column to 1, only one way to reach each cell along the edge. Initialize a DP table of size MXN, fill first row and column with 1. For each cell not on the edge, dpij equals dpi1j plus dpij1. Return dpm1n1. Approach. 2D DP grid. Time complexity. OMN. This line defines the solution class. In Java, all our logic needs to live inside a class, so this is just the container for the algorithm. This is our main method. It takes two numbers, m rows and n columns. The goal is to calculate how many unique ways a robot can move from the top left corner to the bottom right corner of the grid. Here we create a 2D array called DP. Each cell dpij will store the number of unique paths to reach that specific cell. Think of this grid as a map where every square remembers how many ways lead to it. This loop fills the first column with ones. Why? Because if you're in the first column, the robot can only move down. There's exactly one way to reach any of these cells. Pause. This loop fills the first row with ones. Similarly, if you're in the first row, the robot can only move right, so there's only one path to each of these cells. This outer loop starts from the second row. From here on, each cell can potentially be reached from more than one direction. This inner loop starts from the second column. Together, these two loops allow us to fill the grid cell by cell. This is the key rule. To reach cell I, j, the robot can come from the cell above it, or the cell to the left of it. So we add the number of ways to reach those two cells and store the result. Pause. This is the heart of the dynamic programming idea. Finally, we return the value in the bottom right cell. That number represents all the unique paths the robot can take to reach the destination. This closes the method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first initializes the edges of the grid with guaranteed paths, then builds the solution cell by combining paths from the top and left until it reaches the destination. Efficient, simple, and elegant. Test case check. Unique paths using dynamic programming. Let's test our function using this input. M equals 3 and n equals 7. These numbers represent a grid with 3 rows and 7 columns, and we want to count how many unique ways a robot can move from the top left corner to the bottom right corner, moving only right or down. Here's why the solution works. We create a DP table where each cell dpij represents the number of unique paths to reach that position. The first row is all ones because you can only move right. The first column is all ones because you can only move down. Every other cell is the sum of the paths from the top and from the left. And that's exactly what our program outputs, 28. This matches the expected result, confirming that the DP grid was built correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all unique paths through the grid using dynamic programming, efficient, accurate, and reliable. Approach, combinatorial formula. Time complexity, OM plus n. This line defines the solution class. It's the container that holds our method. Here we define the unique paths method. It takes two integers representing the grid dimensions and returns the number of unique ways to move from the top left corner to the bottom right corner. This line calculates two important values. Total is the total number of moves needed to reach the destination, and k is the number of downward moves. The remaining moves will be to the right. Here we initialize res to 1. We use a long type to safely handle large numbers during multiplication without overflowing. This loop computes a combinatorial formula step by step. Since the loop runs k times and k is at most m plus n, the time complexity is O(m plus n). This line updates the result using the combination formula. Each iteration carefully multiplies and divides to keep the numbers small while computing how many unique arrangements of moves are possible. Finally, we convert the result back to an integer and return it as the total number of unique paths. This closes the method. And this final brace closes the class. And that's how this algorithm works. It first calculates how many total moves are required, then applies a combinatorial formula to count all valid move arrangements without building a DP table. Efficient, simple, and elegant. Test case check, unique paths using combinatorics. Let's test our function using this input. M equals 3 and n equals 2. These numbers represent a grid with 3 rows and 2 columns, and we want to know how many unique paths lead from the top left corner to the bottom right corner, moving only down or right. Here's why the solution works. To reach the bottom right cell, the robot must make M1 equals 2 downward moves. N1 equals 1 rightward move. So the path is simply a combination of these moves. In total, the robot makes 2 plus 1 equals 3 moves, and we choose where the downward moves occur. And that's exactly what our program outputs, 3. This confirms that the combinatorial formula is computed correctly and matches the expected answer. Wrap up. So, our implementation is correct. The algorithm successfully uses combinations to calculate the number of unique grid paths, efficient, accurate, and reliable. Unique paths. Let's do a recap. So, we've just solved one of the most foundational dynamic programming challenges, unique paths. This problem isn't just about counting roots in a grid, it's about understanding how small decisions stack up into bigger patterns, a key skill that powers most grid-based DP problems you'll see in interviews. Breakdown recap. Conceptually, the task is simple. Find how many ways a robot can travel from the top left to the bottom right corner of a grid, moving only right or down. Every path you count builds from these 2 possible moves, and our goal is to track them systematically. Assess recap. We realized brute force would explode in complexity, so dynamic programming was the smart approach. The key insight was that every one cell's number of paths depends on just 2 previous cells, the one above it and the one to its left. Once we got that recurrence relation down, the problem became straightforward. Structure recap. We planned it like this. Start with a grid of path counts, initialize the first row and first column to 1 since there's only one way to move along the edges, and then fill the rest by summing the top and left cells. That pattern continues until the destination cell gives us the total number of paths. Implement recap. We implemented the logic cleanly, ran the solution on LeetCode, and everything executed perfectly. No syntax issues, no boundary errors. The DP table built up exactly as expected, and the output matched every test case. Check recap. After running multiple scenarios, all test cases passed successfully. The results lined up perfectly, even for edge cases like single row or single column grids. The logic worked efficiently and consistently. Closing insight. The big takeaway? Unique paths teaches the foundation of dynamic programming, breaking big problems into overlapping subproblems. Once you master this pattern, you'll start seeing the same logic in everything from grid traversal to robot movement to advanced combinatorial DP questions.